The massive explosion is an idea that has laid out the framework for deciphering the universe. It explains the support of current cosmology, as defined by Einstein's theory, known in cosmology courses, as the beginning of the universe's evolution. This huge explosion, often referred to as the Big Bang, occurred approximately 13.8 billion years ago. It sparked the formation of the colossal universe we observe today. Despite the apparent starting point, advancements in cosmology indicate that the colossal explosion was likely not the very beginning. There may have been a stage prior to this enormous event, an important phase that helped shape the universe to its current form. This pre-phase is referred to as inflation or infinite expansion. One of the most fascinating contemporary ideas in cosmology is that, before the intense heat of the Big Bang, the universe experienced unimaginable rapid exponential growth. During this inflationary period, the universe expanded at an alarmingly rapid rate, duplicating its size in an instant. To understand just how extreme this expansion was, consider that if the universe began from a point smaller than an atom, it would have grown to be unfathomably larger than the entire observable universe in a tiny fraction of a second. This expansion took place within a quadrillionth of a second and lasted only briefly, but it played a crucial role in the formation of the universe. After the end of the inflationary phase, the energy driving this expansion was released into the universe. This energy warmed it and led to the creation of matter, particles that would eventually form everything we see today. Many scientists now believe that this inflation was the true precursor to what we call the Big Bang. While the inflation hypothesis is widely accepted in cosmology, it still comes with many unanswered questions. We still don't fully understand how inflation started, what brought it to an end, or how long it lasted. These are critical areas of inquiry for better understanding the universe's beginning. Before evolution, the universe was in an extremely dense and small state, often referred to as a singularity. The evolution of this singularity led to the arrangement of atoms, stars, and galaxies. The possibility of the Big Bang serving as the true beginning is compelling, but today's cosmology paints a more complex picture. Some hypotheses suggest that the universe underwent a phase prior to the Big Bang, during which inflation caused it to grow incredibly fast, by a factor of 1 trillion in a very short amount of time. This brief expansion was fueled by a strange energy field that existed in the void. The energy, once released, transformed into atoms, warming the universe and triggering what we now call the Big Bang. Although the inflationary stage was cold and empty, it set the stage for material production and for the formation of the universe as we know it. More recent theoretical considerations introduced the concept of eternal inflation. According to this hypothesis, inflation did not end everywhere at once, but instead stopped intermittently in various regions, creating pockets, each of which could be its own universe. Our universe, then, may be just one of many, or even an infinite number of universes. If this theory is correct, it would explain why our universe appears so perfectly tuned for life. In a multiverse, every possible combination of physical laws could exist in different universes. We simply happen to live in one where the conditions support life. Though hypotheses like the multiverse and eternal inflation remain open to debate, the foundation of inflationary theory is backed by solid observational evidence. The most compelling support comes from the cosmic microwave background, CMB, radiation, the oldest light in the universe. The CMB was emitted about 380,000 years after the Big Bang, once the universe had cooled enough for atoms to form. At that point, space became transparent, allowing light to travel freely. By studying the CMB, cosmologists can essentially take a snapshot of the infant universe. This light reveals vital details about the universe's origins. Observations, particularly from the European Space Agency's Planck satellite, have captured high-resolution images of the CMB. These images reveal slight variations in temperature across the early universe, variations that align closely with predictions made by the inflationary model. This evidence strongly supports the idea that inflation is not just speculative theory, but a critical part of our understanding of the universe's beginning. To understand both the Big Bang and what preceded it, scientists are trying to unify two major frameworks in modern physics: Einstein's general relativity and quantum mechanics. General relativity explains the behavior of planets, stars, and galaxies on a large scale, while quantum mechanics governs the behavior of atoms and subatomic particles. To answer the most important cosmological questions, such as what the universe is made of and where it came from, researchers aim to create a theory that merges these two frameworks. Such a theory would help us understand not only the Big Bang but also the events leading up to it. The size of the universe is astonishing. Most of the farthest objects we can observe are about 47 billion light-years away, which means the observable universe spans about 94 billion light-years in diameter. At first glance, this seems contradictory. If the universe is only 13.8 billion years old, how can it be so large? The answer lies in the fact that the universe has been expanding since the Big Bang. As it expands, the distance between objects increases, meaning some objects are now farther away than the time it would take for light to travel. Most scientists agree that the observable universe is only a portion of the whole. It's entirely possible that the universe is infinite in size. The part we can see is constrained by the time light has had to travel since the Big Bang. There may be portions of the universe we will never be able to observe. The big question remains, is the universe infinite? What lies beyond what we can see? Scientists don't yet have definitive answers. If the universe is indeed infinite, it would continue forever, without boundary. Even if it isn't infinite, the idea of outside the universe may not be meaningful, as space and time themselves are properties of the universe. Asking what is beyond space may be like asking what is north of the North Pole. Finally, the future of the universe is also a topic of intense study. Current predictions suggest that the universe will continue to expand indefinitely. This ongoing expansion is driven by a mysterious force known as dark energy, which causes the universe's growth to accelerate over time. Dark energy remains one of the greatest mysteries in modern cosmology. Unlike matter and normal energy, dark energy doesn't clump or dilute in the way we would expect. Instead, as space itself expands, dark energy seems to remain constant or even increase in density, leading to a runaway effect. The more space there is, the more dark energy exists, and the faster the expansion becomes. This accelerating expansion raises questions about the ultimate fate of the universe. Several scenarios have been proposed. One possibility is the Big Freeze or heat death, in which the universe continues to expand forever. In this scenario, galaxies drift farther apart, stars exhaust their fuel and burn out, and the universe becomes cold, dark, and lifeless. Matter decays, and all processes slow down as the universe approaches a state of maximum entropy. Another possibility, although less supported by current data, is the Big Rip. If dark energy's effects become stronger over time, it could eventually overcome even the gravitational forces that hold galaxies, stars, and atoms together. In this dramatic end, the universe would be torn apart at every scale, from galaxy clusters down to subatomic particles. Alternatively, there is the Big Crunch hypothesis, once considered a strong contender. If the universe's expansion were to eventually reverse due to gravitational pull, all matter could collapse back into a dense point, possibly triggering another Big Bang in a cyclical model. However, current observations show that expansion is accelerating, not slowing, making this scenario increasingly unlikely. The study of dark energy and the universe's fate is tightly linked to understanding its origin. Many physicists believe that answering questions about the early universe and inflation could unlock the secrets of dark energy. Perhaps the same unknown force that drove inflation is responsible for today's accelerated expansion, though in a more subdued form. In pursuit of these answers, scientists build powerful telescopes, particle accelerators, and space probes. Projects like the James Webb Space Telescope, the Vera Rubin Observatory, and upcoming missions like the Euclid Space Telescope aim to map the universe in greater detail than ever before. By observing the distribution of galaxies, cosmic background radiation, and large-scale structures, we can test our theories and refine our models of the universe. Furthermore, advancements in quantum physics may play a key role in the next breakthroughs. Concepts such as quantum fluctuations, vacuum energy, and string theory attempt to describe what classical physics cannot. These ideas aim to unify the known forces of nature into a single theory, sometimes referred to as the theory of everything. If successful, such a theory could explain not only how the universe began, but why it follows the laws we observe today. Ultimately, the story of the universe, from the tiniest fraction of a second after the Big Bang to its farthest, coldest future, is not just about matter and energy, but about our place in it. The more we learn, the more profound the questions become. Why does the universe exist at all? Why does it allow for life, consciousness, and self-awareness? And is our universe truly unique, or just one of many in a vast multiverse beyond comprehension? These questions may never have final answers, but the journey to explore them drives some of humanity's most ambitious scientific efforts. As we probe deeper into the cosmos, we are, in a way, looking into ourselves, our origins, our future, and the infinite possibilities that lie beyond the stars. Prior to the emergence of dark energy, scientists believed that the universe's expansion would eventually slow down due to the pull of matter's gravitational force. Indeed, There was even a possibility that the universe might stop expanding and begin contracting, resulting in a major crunch. But dark energy appears to be tearing the universe apart more and more swiftly. If this rate of acceleration continues, the universe will never stop expanding. Eventually, it will reach a point where galaxies are so far apart that they can no longer interact. In this circumstance, the universe would transform. Stars would wear out, cold, lifeless, and exhausted. Matter and our worlds would drift apart and eventually rot. This scenario is known as the major heat or freeze death of the universe. The story of everything, from the massive explosion to its final state, is one of the most improbable, important, and intricate stories in science. Despite the fact that we've gained an extraordinary amount of knowledge about the universe, based on the theory of expansion as well as investigation of the extensive cosmic microwave background, there are still questions. Why did expansion begin in the first place? How will it finish? Is there a space beyond the visible universe? Is there a multiverse? And how many additional universes exist? As research continues, scientists are focusing on the universe by employing new ideas and advanced hypotheses to connect quantum mechanics with general relativity. Without this connection, we will never fully understand the deeper truths of the universe. The journey to comprehend the mysteries of the universe continues. Each discovery helps us get closer to addressing profound questions about our existence. The study of the structure and origins of the universe is more than just a logical pursuit. It also brings up philosophical inquiries about the nature of our presence and our place in the cosmos. One of the most important topics in cosmology is dark matter, which is accepted to make up approximately 27% of the mass and energy of the universe. Unlike normal matter, dark matter does not absorb or reflect light, making it invisible and observable only through its gravitational effects on visible matter. Understanding dark matter is essential for comprehending the development and evolution of the universe. Research and observation have revealed some properties of dark matter, but its specific nature continues to be elusive. Only a few candidates have been proposed, including weakly interacting massive particles, WIMPs, actions, and other exotic particles. However, no direct evidence of dark matter particles has yet been found, and the search continues, through terrestrial experiments, astronomical observations, and simulations of how dark matter influences the large-scale structure of the universe. Another key area of exploration is dark energy, the force responsible for the accelerated expansion of the universe. Dark energy makes up about 68% of the universe. Its discovery was unexpected and has led to numerous cosmological hypotheses, including those involving dynamic and constant fields. Understanding dark energy is vital because it will determine the ultimate fate of the universe. Researchers are studying its effects on cosmic structures and trying to figure out whether it remains constant or changes over time. Despite advancements, dark energy and dark matter remain some of the most mysterious aspects of the cosmos. Investigations into how structures form in the universe provide significant insight. Observations and data from enormous cosmic webs and galaxy clusters have shown how matter clumps together under the influence of gravity. These mysterious structures are now being modeled with the help of supercomputers, which assist scientists in understanding how they evolved over tens of billions of years. Astrobiology has also progressed alongside cosmology. Scientists are working to identify the conditions necessary for life on other planets. The discovery of exoplanets, planets that orbit stars outside our solar system, has exploded, with thousands found in recent years. Some of these exoplanets lie in the habitable zones of their stars, where conditions might allow for liquid water to exist. By studying these distant worlds, researchers hope to learn more about the potential for life elsewhere in the universe and the factors that make a planet suitable for life. Finally, the role of fundamental physics in cosmology cannot be overstated. The mission to find a unified theory that connects general relativity and quantum mechanics continues. Theories such as string theory and loop quantum gravity aim to bridge the gap, offering explanations for phenomena like the early universe and black holes. As our technology improves, so too does our ability to observe and understand the vast and unique features of the cosmos. Space telescopes like the James Webb Space Telescope are revolutionizing our view of the universe by providing incredible detail about distant systems and cosmic events. As we get closer to unraveling the mysteries of how the universe is structured and what its final destiny may be, we find ourselves on a journey that is as philosophical as it is scientific. The universe is a complex web of logical puzzles and existential reflections. From the fundamental forces to the search for extraterrestrial life, our exploration is more than just a scientific endeavor, it's a way of life. It is a testament to human curiosity, perseverance, and our enduring fascination with the cosmos. As we try to answer these profound questions, we also deepen our appreciation for the incomprehensibility and complexity of the universe. Our understanding of the universe is still in its infancy. Every answer seems to open the door to dozens of new questions. We now realize that what we once believed to be a straightforward universe governed by a few physical laws is, in fact, a dynamic, mysterious, and multi-layered existence, one that challenges not only our scientific assumptions but also our philosophical and spiritual beliefs. One of the more recent and compelling frontiers in cosmology is the study of the early universe, specifically, what happened in the first fractions of a second after the Big Bang. During this unimaginably brief period, the universe expanded at an exponential rate in what is known as cosmic inflation. Understanding this process may reveal clues about the fundamental nature of space, time, and even the origins of the laws of physics themselves. Then comes the question of symmetry and imbalance. Why is the universe made predominantly of matter, when the laws of physics suggest it should have produced equal parts matter and antimatter? This asymmetry, though essential for our existence, remains one of the most pressing and perplexing mysteries of modern physics. Simultaneously, physicists are probing the depths of black holes, not just as gravitational monsters but as potential gateways to new physics. Black holes, especially those found at the centers of galaxies, may hold clues to the unification of general relativity and quantum theory. Some even speculate they could be tied to the birth of new universes or act as bridges between dimensions. As our tools grow more precise and our data more abundant, collaboration between disciplines becomes essential. Cosmology now intersects not only with particle physics and quantum mechanics but also with fields like information theory, artificial intelligence, and even philosophy. These collaborations are forming new pathways to understanding, pushing the boundaries of what we thought was knowable. In recent years, the idea of the multiverse has gained traction, not as science fiction, but as a serious scientific hypothesis. If our universe is just one of many, each with its own set of physical laws and constants, then the questions we ask about fine-tuning and cosmic design take on new dimensions. Are we a rare cosmic accident, or is life an inevitable consequence in an endless sea of universes? Still, with all this knowledge, we remain tiny observers on a pale blue dot, staring into the abyss with curiosity and awe. The universe may not offer easy answers, and its destiny might be beyond our control, but our quest to understand it defines something profound about what it means to be human.